Hello everyone, welcome to this session. We'll solve the problems in impact of jets, and this is your first problem. A jet of water 75 mm in diameter issues with a velocity of 30 meters per second and impinge on a stationary flat plate. Okay, it is a stationary one, and that too a flat plate. Okay, stationary and the flat plate, which destroys its forward motion. Don't confuse with this forward motion. Okay, it is still a stationary one and still it is a flat plate. There won't be any motion for the plate. Find the force exerted by the jet on a plate and work done. You require to find the force and the work done also. Okay, and the work done. Clear? And we'll start the solution. And first write the given data, which is like diameter of jet. Okay, the small d, which impinge on a flat plate is 75 mm. If you convert that into meters, it will be like 0.075. Next, the given data is velocity, which is 30 meters per second. And the next one, for this we require the force, right? And from the impulse momentum principle, we know that the force is equals to mass into the initial velocity minus final velocity, right? v1 minus v2. And now what is v1? The velocity with which the jet is striking the plate. And what is v2? The velocity with which the jet after striking the plate. And now what is m dot, like mass per second? Rho a v, right? And we know what is density of water, and we know what is velocity, and we require the area, right? And from this diameter, you know the area of jet, right, which is like pi by 4 d square, and that is area of jet, which is like pi by 4 d square. If you substitute this d value in meters here, you will get the area. And now finally the force, which is equals to rho a v square, and these will be 0, right? This velocity after impinging the plate will be 0, and the mass is rho a v, and the initial velocity is v, and the formula is rho a v square. And if you substitute all the values, then you are going to get the force impinge on the flat plate when it is stationary, right? And now the work done is nothing but here 0. Why? Because it is a stationary plate, the plate is not moving, so the work done is 0. Clear? We'll see the next one, and this is your second one. Here, a jet of water of diameter 50 mm moving with a velocity of 40 meters per second strikes a curved fixed symmetrical plate at the center. See, these are the very important, like curved, it is a curved plate, and that too it is a symmetrical, and that too the jet is striking at the center. So for this we have direct formulas which we discussed in the previous sessions, right? We'll see that. And now in this problem we have to find the force exerted by the jet of water in the direction of the jet if the jet is deflected through an angle of 120 degrees, and this is a important in this problem, at the outlet of the curved plate. After jet striking the plate, it is deflected to an angle of 120 degrees, right? Clear? We'll see the given data first, and later we'll see the diagram of this. Okay, and the diameter is 50 mm, or else we can convert that into meters, and the area is pi by 4 d square, and you are going to get this value, and the velocity with which it is striking at the center of the curved plate is 40 meters per second. See, this is your jet which is striking at the center of your curved plate. After striking this, okay, it is deflecting through how many degrees? It is the deflecting through angle of 120 degrees, but this angle is not 120 degrees. Clear? see this angle of deflection. Actually, the jet after striking the plate, it has to move in this direction, but it is deflected through an angle of 120 degrees. This is your 120 degrees. Clear? And now we require this theta. Okay, we require this theta, and that you're going to substitute here, which is the angle after striking the plate. And now this is the angle of jet which is after striking the plate. So for this, what you're going to do, this is 120, right? From 180, if you neglect this 120, what you're going to get, okay, the angle here you can see the angle of deflection, which is 180 minus theta. It is nothing but 180 minus theta is equals to 120 degrees. That means this particular angle, which is 180 minus theta, is 120 degrees. And if you resolve or if you simplify this, what you're going to get, the theta value is 60 degrees. That means this value is 60 degrees, and from this total figure, and these two thetas are alternate or similar one, okay, this theta will be 60 degrees. Clear? And from the previous sessions, what we discussed, for the curved fixed stationary plate at the center, and this is your formula for the force which is impinged on a curved plate which is symmetrical, and that too the jet is striking at the center. And this is your formula, which is like rho a v square 1 plus cos theta. If you substitute all the values, you are going to get this, the force which is impinged on this. And now what is this rho? Density of water. The density of water is 1000. Area we already got from here. Okay, the velocity is already given, which is like 40, and the square we substituted here, and 1 plus cos theta, and here the theta value is 60 degrees, what we resolved. Clear? And the next one, a jet of water from a nozzle is deflected through 60 degrees. Deflected through 60 degrees. It is not like previous one. We'll see here. From its original direction by a curved plate, but he's not saying any symmetrical one here. You have to concentrate on it. Here it is a curved plate, but not a symmetrical, which enters tangentially without shocks with a velocity of 30 meters per second and leaves with a mean velocity of 25 meters per second. So he is giving like inlet velocity and the outlet velocity. Now we require to find the discharge from the nozzle is like 0.8 kg per second, which is like here it is like m dot is directly given. Calculate the magnitude and the direction of the resultant force. We'll see this in the figure, what is this resultant force, and we require the magnitude and we require the direction. That means we require what? Direction, which is like theta we require. Then what is this 60 degrees? He is asking about the direction, which is like theta, but still we have 60 degrees. So what is this 60 degrees? We see that on the way, if the vane is stationary, okay, the vane is stationary, but he is not mentioning that it is whether it is symmetrical or unsymmetrical. Okay, so we'll see what is this 60 degrees now. First we'll see the given data. He given inlet velocity, outlet velocity, and this is your m dot. Okay, don't confuse. Why I'm saying m dot means, what is the units with mass? Kg. M dot is mass per second. Clear? And the next, this is your figure. Okay, so he said only about the curved and about the stationary, but he not mentioned anything that like whether it is striking at the center or a tip. He just given that in a original direction. Original direction will be horizontal. Okay, it is horizontal, but not at the like a this. He is not giving. He is not mention any angle, right? So that's why you're taking like a horizontal one. And now this jet will deflect through an angle of 60 degrees. Clear? And this is deflected through 60 degrees. Now the velocity which is leaving is like 25 meters per second. It is inclined with the horizontal of 60 degrees, and we require the velocities in horizontal direction, in the vertical direction. And for the horizontal direction you have v cos theta, and here we have v sin theta. So these are the two components of your velocities, which is like if it is 25, it is like 25 cos 60, because we have already 60 degrees deflections. And now this is your vertical component of the velocity, which is like 25 sin 60. And now uh, from the impulse momentum equation we have the force in x direction equals to mass per second. It's already given. And the v in x direction, that is initial velocity in x direction, and the final velocity in the x direction. See, here he given the velocity which is like 25. It is angular, I mean the velocity in a 60 degrees, but it is not the velocity in the x direction. We have to resolve that velocity in the x direction like this, which is like 25 cos it. Like if you substitute those values, like fx equals to mass per second, which is like 0.8, the velocity in the x direction is 30, the velocity in x direction of the outlet is 12.5 if you resolve 25 cos 60. And now we require the magnitude. Okay, so for that sake what you're going to do is, uh, we know the resultant is nothing but it's a magnitude of the resultant force. Okay, so for that sake we are finding the Fy, which is, first we'll see what is the resultant force on the vane. See, this is your resultant force on the vane, which is like square root of fx square plus Fy square. Okay, we know what is the we already find this fx. Now we'll see what is this Fy, mass per second into the velocity in y direction initially, the velocity in y direction finally, that which is like outlet. Like this is your mass per second, and this is your velocity initially in the y direction. So in the y direction there is no velocity, so it is 0, but in the velocity at the outlet in the y direction is 25 sine 60. Okay, if you resolve this, what you're going to get is this one. If you substitute fx and fy in the resultant, what you're going to get is 25 is the magnitude. And now what is the direction? Tan theta is equals to the force in the y direction divided by the force in the x direction. If you simplify in these values from the above, what we concluded, that equals to this one. And finally the theta value is 51 degrees 2.86 minutes. Okay, and the next one, a jet of water having a velocity of 35 meters per second impinge on a series of vines. Okay, you have to concentrate on this series of vines moving. These are not the stationary, moving with the velocity which is like 20 meters per second. It's a vane velocity but not the jet velocity. Jet velocity is this one, which is like 35 meters per second, and this velocity is vane's velocity, which is like small u. Jet makes an angle of 30 degrees to the direction of motion of mains. 30 degrees to the direction of motion of mains when entering, and leaves it an angle of 120 degrees, which is like this is like angle of deflection. And draw the triangles of velocities at the inlet and outlet, and find the angles of the vane tips, vane angles, which is like theta and pi, so that water enters and leaves without shocks. And work done per unit weight. It is not work done per second, it is per unit weight. That means the work done per weight is mg. You know, water entering the veins. And the efficiency, what is efficiency? Outlet by inlet, what is the outlet? The work done. And what is the inlet? Kinetic energy. Okay, and now first we'll see the given data. And this is the velocity which is entering, and this is the vane velocities. See, here when it is giving like a u1 equals to u2, it is a frictionless. There won't be any frictions. It is a friction free or no friction. And we have the alpha, which is the jet inclined with respect to the tip here. That means alpha equals to 30 degrees. Now what we require to find is this theta and pi. Now what is beta? It's already given, like it is like 120. Okay, 120 with the direction of motion of the vane, it is 120. Then what is this particular angle? We'll resolve that. From the previous we know it is like 180 minus theta is equals to 120. If you resolve that, the beta here is 60 degrees. In the previous case we seen here like theta, now it is like beta. Don't confuse with this theta and this theta. In that problem that theta is different and here this theta is different. Okay, now to get the theta value, where is that theta? Here the theta value is there. So if you know the components of VR1 and this is VF1, okay, if you know the VR1 and the VF1, you will get theta value. You will see that. See here, from this particular triangle, see, now from this particular figure we can able to find this theta, right? So before that we require this particular value, right? For that we require this VW1 from the total triangle. If you take this alpha, okay, which is like cos alpha, then you are going to get VW1 divided by V1, which is like here cos alpha equals to VW1 divided by it is V1. So you can take this value here. So now what you're going to, if you just substitute the values, you're going to get VW1. Now what is VF1? This is your VF, which is like flow velocity. Now from the total figure, if you take the sine alpha value, then you're going to get this flow velocity. And now from the tan theta of this particular figure, is VR1 divided by VW1 minus U1, right? This one, okay, flow velocity divided by minus 1 VW1 minus U1. And if you substitute the values from these two values, you're going to get the theta, which is like theta equals to tan inverse of 1.697, that equals to 60 degrees. And still we require this pi value, and after that we have to find this work done per weight and the efficiency. Now from the inlet velocity diagrams, and that too from the sine rule, if you follow this, you're going to get this VR1, which is relative velocity. And the next here, the VR1 is equals to VR2, which is like when there is no friction, then your VR1 is equals to VR2. When there is no friction, VR1 is equals to VR2, and even U1 is equals to U2. Okay, and now these are the from the outlet velocity triangles, and that too from the sine rule. If you take this and simplify, what you're going to get is this pi value. Okay, and this one is from your outlet triangles, and that too following the sine rule, you're going to get this. And if you solve that, what you're going to get is this pi. Clear? And now the work done per weight of water entering is equals to, see, this is your formula which you're already having for the series of vanes, 1 by G into VW1 plus VW2 into U1. And you know what is VW1, which is like a wheel velocity, and this is your blade velocity. Now to get this VW2, we'll see the triangles, velocity triangles of the figure. See here, from these particular outlet triangles, okay, what we require is this VW. Alright. Now what is this VW? If you want this particular value, okay, first what is this total value? VW2 plus U2. VW2 plus U2. Right? See here. If you bring this value towards this side, what you're going to get is VW2 minus U2, and that equals to divided by VR2, that equals to cos pi. Cos pi is nothing but VW2 minus U2 divided by VR2. Right? Now see here. This is your VW2 U2 and this is your VR2. Okay, so from this total triangle, what you're going to get is cos pi is equals to VW2 minus VR2. Okay, now what you got is this cos pi. If you simplify this by sending VR to this side and sending this negative U2, sorry, this is positive U2 to this side, what you're going to get is VW2. And if you simplify all the values or substitute all the values here, you're going to get the VW2. And what is the work done per unit weight? And we already have the formula, which is like 1 by G. This is VW1 value, this is VW2, which is like wheel velocity of inlet, wheel velocity of outlet, into this is the blade velocity. Clear? And if you simplify this, you're going to get this value. And what is the efficiency? Work done per kg divided by energy supplied per kg, which is like half mv square, and that too, this is per kg, so that's why it is v1 square by 2g. Clear? And if you simplify this, you're going to get like efficiency of 99.74. Clear? Thank you.